Right. Okay, so let me recap, or let's see what we are going to discuss in this module. So first, we will be continuing with our boundary conditions. We have looked only at one boundary. So using that boundary conditions, we are going to derive for other types of boundaries. And next, we look at Laplace and Poisson's equations. And then we will look some basic stuff about magnetostatics. Okay. So to recap the boundary conditions, we told that if there is a dielectric boundary, then we say that the electric tangential component of the magnitude of the electric field in both the boundaries will be equal, or in both the mediums will be equal. The electric flux density is related as epsilon 1, or I would say epsilon 2 d2t is equal to the magnitude of epsilon 1 d1t. Sorry, again, this is epsilon 1, this is epsilon 2. Okay. Similarly, we also derived for normal components, which we said as the magnitude of d1n minus d2n is equal to the surface charge density rho s, and then if rho s is equal to 0, then both will be equal. We also saw that the magnitude of epsilon 1 e11 n minus magnitude of epsilon 2 e2n is also equal to rho s. So if rho is equal to 0, which means these components are equal. Okay. So this is what we have seen in the dielectric boundary. Now let's consider another boundary, which is conductor dielectric boundary. Okay. So in the conductor dielectric boundary, you have a dielectric in one part, or dielectric medium is there in one part, and a conductor is there in another part. And we have seen that for a conductor, or inside a conductor, the value of the electric field is 0. Right? So if the value of electric field is 0 inside a conductor, then its tangential component and the normal component should be equal to 0. Right? So if I substitute in the above equations, right? So you see the magnitude of E1t is equal to the magnitude of E2d, which is 0, because this is E2t and this is E2n. Okay. So basically I am substituting in this equation, this one. Okay. And then the magnitude of d1t will also be equal to 0, because electric field is 0, which means electric flux density is also 0. Then the magnitude of d1n minus something, which is 0, should be equal to rho s, and the magnitude of epsilon 1 e1n minus 0 is equal to this. Okay. So use from the dielectric boundary, you can deduce the boundary conditions for conductor dielectric boundary, because for a conductor, the important thing is the electric field is 0. So if you substitute these values in the dielectric boundary conditions, then you will get the conductor dielectric boundary conditions. Okay. So if rho s is equal to 0, which means surface charge density is 0, then the magnitude of d1n is equal to 0, and the magnitude of e1n will also be equal to 0. So you see that in a conductor dielectric boundary, all the fields gets vanished. In dielectric, there is field, but once you cross to conductor, all the fields will get vanished. This is regarding the conductor dielectric boundary. I can also have a relation between conductor free space boundary, okay, in which you have a conductor in one side. Instead of dielectric, you have a free space. So what is specialty of free space? For a free space, the value of permittivity is equal to epsilon 0. So epsilon 1 equal to epsilon 0. So again, you can reduce or deduce these values from the dielectric boundary conditions. Okay. So wherever there is epsilon 1, you substitute for epsilon 0, you will get the answer. Okay. So I'm just giving this as a homework for you to work it out. Okay. So you can just want to look at these equations and substitute epsilon 1 is equal to epsilon 0 in this. So this will give you the conductor free space boundary conditions. Okay. So this is regarding the boundary conditions, electrostatic boundary conditions to be specific. And we have reduced all the boundary conditions, which we will make use in the next module when we discuss Maxwell's equations. Because when the electromagnetic wave propagates through a medium and crosses a boundary and reaches another medium, the electric field and magnetic field will change. And how much change it is there will depend on these boundary conditions. So make sure you understand how the boundary conditions are derived. Okay, the boundary conditions are very simple. There is no complications in boundary conditions, which we saw earlier. At least if you understand the results of the boundary condition, that is more than enough. Okay, fine. Now let's move on to the Poisson's and Laplace equations. Okay, so Poisson's and Laplace equations are second order equations, differential equations, which we can use to find out the vector potential. And finally, using vector potential, you can find out the electric field, even the charges. Okay, so let me derive the equation first. Okay, and it is derived from Gauss law. Okay, and this is for linear isotropic medium. So what do you mean by an isotropic medium? Isotropic medium means the properties of the medium in all directions is same. Okay, for example, permittivity. If you look at any point in the medium, or if you go through any direction in the medium, then the permittivity remains the same. For example, something like this. If you go in direction, in this direction, in this direction, the properties of the medium remains the same. Such a medium is called as a isotropic medium. And linear medium means the properties vary linearly, means there is no quadratic variation. Fine. So the derivation is very simple. From Gauss law, you have del dot D is equal to rho v, which means del dot epsilon E is equal to rho v, which we have seen because D is equal to epsilon v. And we know that E can be written as minus del V, where V is the potential. So if I substitute this, I can write del dot minus epsilon del V is equal to rho V. Now, if you are considering a homogeneous medium, or I would say the del or the epsilon 1 is a constant because this is the permittivity of the medium, which is depending only on the medium, is a constant. So I can take del out. So I can take epsilon out. So I can write this as minus del dot del V is equal to rho V by epsilon, implies I can write del square V is equal to minus rho V by epsilon. And this is called as Poisson's equation. Although the derivation is very simple, it can be used in deriving many things. So this is called as Poisson's equation. Okay. Now here we have assumed one thing. The value of epsilon is same in all parts of the medium. Or we say this is a homogeneous medium. Implies epsilon is same in all medium, which might not be correct in all the case. Okay, so if the epsilon value is not same in all parts of the medium, then you should make use of this equation. This is for inhomogeneous medium. Okay, now if I say rho v is equal to 0, which means the volume charge density is 0, I can write this equation as del square v is equal to 0. And this is called as Laplace equation. Okay. So the derivation is very simple. You derive it from the Gauss law, and you can just directly substitute the values to derive the values. Now I can write these equations in Cartesian, in cylindrical and spherical coordinates and Cartesian coordinates. So I can write this as del square v by dou x square, sorry, dou square v by dou x square plus dou square v by dou y square plus dou square v by dou z square is equal to 0. This is in Cartesian coordinate system. 1 by rho dou by rho into dou v by dou rho plus 1 by rho square into dou square v by dou phi square plus dou square v by dou z square is equal to 0. This is in cylindrical coordinates. And finally, in spherical coordinate is 1 by r square dou by dou r into r square dou v by dou r plus 1 by r square sine theta dou by dou theta sine theta dou v by dou theta plus 1 by r square sine theta, sine square theta, sorry, dou square v by dou phi square is equal to 0. Okay, so these are in different coordinate system. So the first one is in Cartesian coordinate system. The second one is in cylindrical coordinate system, and the last one is in spherical coordinate system. Okay. Now, if you look at the equation, you see it's actually dou square by dou x square, or dou by dou rho into dou v by dou rho. So it's basically a second order differential equation. And it can be possible that this equation can have multiple solutions. But there is a theorem which states that the solution to Laplace equation is unique. Okay, and this is called as uniqueness theorem. We are not going to look at the proof of the theorem, but this is a theorem which says that although the equations are second order differential equations, it can have multiple solutions, but the solution to the Laplace equation is unique. Like it will have only one and only one solution. This is the uniqueness theorem, right? So if you look at the Laplace equation, you have the equation in terms of potential, which is B. And equation means there should be a solution. So once you find the solution, you get the solution of the potential of the system. From the potential, you can always calculate the electric field. From the electric field, you can calculate the electric flux density and even the charge. Okay, so using a single equation, you will be able to find out many parameters of the electrostatic field. Okay, and there is a steps for finding the solution. Okay, so I would say general procedure for solving Laplace or Poisson's equation. Okay, first thing you want to do, you can solve the equation by direct integration, either by direct integration if the potential V is a function of one variable, or by separation of variables if V is a function of more than one variable. That's the first step. Second step, if you should apply the boundary conditions, for example, when you do integration, you will get a constant. Now, if you want to find the constant, you need to say that, okay, at V is equal to 0, this is my value. At V is equal to this much, this is my value. So that is called as a boundary condition. So apply boundary condition to find the unique solution of V. Now you got the potential. Now you can find E is equal to minus del V, comma D is equal to epsilon E, you can find both the electric and electric flux density. You can also find, if it is needed, you can find the charge Q induced on a conductor. Inside the conductor, like over the surface of the conductor, you can get the charge by Q is equal to integral rho s ds, where rho s is equal to the normal component of n. So this is an optional step, but usually we'll be able to find out the electric field. Okay, so I'll give you a tutorial on, or I'll solve one problem on how we can apply this to find out the electric field and the electric flux density. Okay, so this completes our electrostatics. This was our last topic. There is one more topic regarding the capacitance in some of the materials, which I will give you as an assignment, which you can refer book and do it as a and submit it as an assignment. Okay, so I think that is a very easy part. Fine. Next, let's move on to magnetostatics. Okay, so till now we have studied about point charge, or whatever is we have dealt with is with regard to a static charge, and because of the static charge, what are our things which is happening around it, so that it can create force on another charge, it can create a field, it can create a potential if you move the charge, and we also found the Gauss law regarding the electric flux density, and we derived an equation for that, and we found out the Laplace and the Poisson's equations, etc., etc. So what happens when the charge moves? So magnetostatics deals with movement of charges, or do you say current? Current, you can say I is actually the rate of change of charge, dq by dt. So for unit time, how much charge is getting changed? That is basically the current. And movement of charge, time varying charge will produce, time varying movement of charges will produce magnetic field. Okay, and the magnetic field is denoted by H, and it is also a vector. Okay, similar to the Coulomb's law in electrostatics, we have a similar law in magnetostatics, which is called as Biot-Savart's law. Now, in using Coulomb's law, we found the force between any two charges. Using Biot-Savart's law, we are going to find the differential magnetic field, the small magnetic field caused by a small current element. Okay, so the Biot-Savart's law gives, let's say, if there is a conductor like this, okay, and I need to find the magnetic field at this point P, fine, and the conductor is carrying some current I. So if I consider a small strip dl, or small current strip di. Then if I draw a straight line from this small current strip to the point P where I want to find the magnetic field, and let's say this line makes an angle alpha with the wire, then according to the Biot-Savart's law, the small differential magnetic field induced at the point P due to the differential current di is proportional to the product of the current through the wire, which is I, or I, the product of the current and the differential element dl. So this is not di, this is actually dl, which is a vector. Okay, the product of the current and the differential length dl, and the sign of the angle between the differential length and the line joining the point, it is inversely proportional to the square of the distance from the differential element to the point P. R is the distance between the dl and the point P, which implies I can write my small differential magnetic field at point P is equal to some constant which we call as 1 by 4 pi into I dl sine alpha by r square. Okay. Now, if you look at the equation I into dl into sine alpha, this basically looks like a cross product because there is a sine term coming. Okay. So I can write this equation dh in terms of a vector as the current I into dl cross ar cap by 4 pi r square. Okay, because dl is a vector. The direction of dl is tangential to the line. So each time you have a dl, the direction changes, although the dl value will be same. And ar cap is the unit vector along the r direction. Okay, so this will give you the differential, which is dh. If you want to find out h, you want to integrate it over the line. So basically, the value of h is equal to the integral I dl cross ar cap by 4 pi r square. Remember, ar cap is a unit vector whose magnitude is 1. So ar cap is have the magnitude equal to 1. Okay, so this is how you find the magnetic field at any point P. So the point P has a magnetic field component, magnetic field which is caused by all these differential elements here. If you basically add it up by all these differential length elements, you will finally end up getting the magnetic field at P, which is basically we are doing the integration. Okay, now the magnetic field H is actually a vector. It is not a scalar, it is a vector. Because you know the cross product will always give you a vector. So what is the direction of H? The direction of H is, if you curl your finger along the path in which the current is moving, then the direction where the thumb points gives you the direction of the field. So let me try to draw. I am not sure whether I will draw it correctly. So assume that there is a current carrying wire like this, which carries a current I. Okay. Now let's say you, okay, this is on trial basis. I'm not sure whether I'll be able to draw it properly, but anyway, I'll try it. Let's say you curl your finger like this. Okay. So the thumb points in this direction, right? So I'm very bad at drawing. Okay. So you're curling your finger in the where the, or you can do it another way. You point your thumb in the direction of current, and the direction in which you curl your finger will give you the direction of the magnetic field. Okay. So you see that the magnetic field is in a circular direction because when you curl the finger actually rotates around that current element. So basically your direction of magnetic field here is in this direction. Okay. Fine. So similar to we have the line charge, surface charge, etc. In magnetostatics, we have the current is in amps. There is the surface current density, which is in amps per meter, and there is J, which is R vectors, which is volume current density, which is amps per meter square. So here, if you note that the surface current density is amp per meter, it is not amp per meter square. So if you multiply the surface current density with the differential length element, and if you integrate it, you will get the total current. Similarly, if you multiply the volume current density with the surface area, not the volume, and if you integrate it, you will get the total current. Okay. So these are the different current densities available in magnetostatics. Okay. Now, if you consider let's say this is Z axis, and let's assume that there is a straight filament conductor placed here. Okay. Something like this. I want to find the electric, or sorry, the magnetic field at this point P. Okay. So let's say this is A, this is B. Okay. So what I need to do, if you want to apply the Biot-Savart's law, you should consider first a small strip element here, which is DL. You draw a line from this to P, and let's say this vector is R. Okay. And then we can say that, okay, let's say this is origin, and let's say this is at a distance Z from origin. Let's say this distance is, let's say, rho. Okay. And let's assume that it makes an angle alpha here. Let's say this is alpha 1. and this makes an angle alpha 2. Okay. Now, the value of electric field H is given by, will not be going to derivation. The current I, which is flowing through this, so the current I is flowing, divided by 4 pi rho, which is the distance of the point from the z axis, into cos of alpha 2 minus cos of alpha 1 into a phi. Okay. Now, if the conductor, which is this, is semi-infinite, implies you say that B is at infinity and A is at 0, implies my alpha 2 is 90 degree and my alpha 1 is equal to 0 degree. So your magnetic field H is equal to I by 4 pi rho A phi cap. Okay. Now you see that this is A phi cap, which means that it is along the direction of phi. We have seen in when we looked at cylindrical coordinate system how is the direction of phi. Okay, so direction of phi is the angle it makes with the projection over the xy plane. The x-axis makes with the projection, that is called as phi. So phi is along, you can say, as the, if you consider a cylinder here, along the surface of the cylinder. Okay, so this is the electric field due to a small current carrying element, which is basically a conductor. Okay. So this is about Biot-Savart's law. Now let's look at the Ampere's law, which you might have studied all through your +2 classes and the first and second years of your BTech. So Ampere's law states that the line integral of the magnetic field H around a closed path is the same as the net current I enclosed by the path. So what does it mean? Let's say I have a conductor which carries current I. Let's say I have some closed path like this. Okay. And if you consider any small strip dl here, and if you want to find out the magnetic field around this closed path, then the Ampere's law states that the line integral of this closed path of the magnetic field dl is equal to the charge enclosed by the path. So you see the charge enclosed by this path is I, or I would say I enclosed. So if I have another charge element here, okay, let's say this is I1, it will not have any influence on the magnetic field of this closed path, because this closed path encloses only I encode. Okay, so this is what Ampere's law states that. And using, just like we have Gauss law, the Ampere's law is similar to that of Gauss law in electrostatics. And in Gauss law, whenever we want to find the electric field or electric flux density, we consider a Gauss surface. Similarly, whenever we want to find a magnetic field, we can always consider amperian surface. Okay. So now, if you look at this equation, this is a line integral. And using Stokes theorem, you can relate a line integral to a surface integral, which means I can write integral h dot dl is equal to a surface integral del cross h dot ds. So I can substitute del cross h dot ds is equal to the I enclosed. And we have already seen that the surface current density J is ampere per meter, which means if we integrate, so if we integrate J dot ds, it will give you my current. So if I want to find I enclosed, I can write this as integral J dot ds. So there is ds in both the right hand side and left hand side. So if this equation should be equivalent, then I should have del cross h is equal to j. And this is an important equation, which we will make use of when we derive Maxwell's equations. So the cross product of magnetic field will give you the current density. So if there is no current density, basically del cross h is equal to 0. Okay. And as an application of the Ampere's law, you can look at infinite line current. Okay, that means assume that along the z axis there's a current which is infinite. It goes up and down. Let's say I want to find this magnetic field at a point P in y axis because of this current I. So what we do is we will construct an Amperian surface like this. Okay. And then we will say that let's take a small element dl here. And then we will find out, we will know that integral of the magnetic field dot the dl is equal to the current enclosed, which is I. So using this, we can derive the equation of the magnetic field at the point P as I by 2 pi rho a phi cap, where rho is the distance from the origin or distance from the current element I to the point P. This is rho. Okay. Similarly, I can find out infinite sheet of current. Okay. So what we do is, let's say I have an axis like this. Okay. And let's say there is a sheet over this z axis. Okay. And this sheet has some amount of current density over this. Let's say it is along the y direction, which means k is equal to some ky ay. Okay. So you want to find the current density or the magnetic field induced because of this sheet of charge. So what we will do is we will construct an amphibian surface, which is basically, I am not sure whether I'm able to draw it, something like this. And we say that, okay, direction of the surface is like this. Okay. And then we will find out the magnetic field. And the magnetic field induced is given as 1 by 2 K cross A, where AN is perpendicular to a sheet, which is in the Z direction. So this is Z, this is Y, this is X. So we are not going into the derivation of this, but make sure you understand the formula so that we can make use of the formula in our problems. Okay, this is for infinite sheet of current. So those who have joined late, I have already told that I'll be taking some 5 or 10 minutes of time to finish this module. Okay, so I don't think we'll be able to finish this module, but anyway, we'll see as much as we can. Fine. So this is regarding the Ampere's law. We'll be making use of, we'll be collecting all these laws in electrostatics and magnetostatics to derive Maxwell's equations. So make sure you understand all this law. The next one is magnetic flux density. It is denoted as B is equal to mu 0 into H. And mu 0 is called as permeability of free space. Okay, just like we have D is equal to epsilon 0 E, we have B is equal to mu 0 H. If we are using any other medium, so other mediums, you have mu, which is equal to mu 0 into mu r, where mu r is the relative permeability. And mu 0, the value is given as 4 pi into 10 raised to minus 7 Henry per meter. And the unit of magnetic flux density is Weber per meter square or Tesla, denoted as T. Okay, so magnetic flux density is the magnetic flux per unit area. So if I integrate magnetic flux density over the surface area, you will get the total magnetic flux. And the total magnetic flux, so basically the magnetic flux density should have some direction, and the magnetic flux direction is, you can say it is a line along which, let's say there's a compass you place somewhere in the magnetic field, and it is a line along which the needle of a magnetic compass will orient itself if it is placed in the magnetic field. Okay, so for example, let's say I have some current carrying conductor. So dot means it is into the plane of paper. So it is coming out of the plane of paper. This is I. So if you place a compass around this one, you will see that the needle of the compass will move something like this around. Okay, so it will be something like this, moves like this. And this is the direction of the magnetic flux density. Okay, and you see that if you look at electrostatic flux, it is open, means it will start from a point charge q and it can radiate from this charge q. But magnetic flux, the magnetic flux lines are closed, which means where it starts, it will end. It is not open like electrostatics. For example, if I have a magnetic material like this with the north pole and the south pole, the magnetic flux line will start from the north and ends in the south. Similarly, it can have multiple flux lines like this. Okay, so they are always closed. Now, if I break this one, it will create a new magnetic, two new magnetic materials with north pole and south pole, with new north poles and south poles. If I break again each of them, it will create a new magnetic material which will have both north pole and south pole. So whenever you do change the magnetic material, it will create a new magnetic material with same properties. And for all these things, you will have a closed magnetic flux lines. Which means if you consider a surface, the total flux through that surface is always zero. Let me write that. Total flux through a closed surface in a magnetic field is zero. Why? Because magnetic flux lines are always closed. You will not have individual flux lines just like we have in electrostatics. So because of they are closed, the total flux is zero, or total flux through a closed surface is zero, which means phi will be is equal to zero. That is integral b dot ds. Now by divergence theorem, integral b dot ds is equal to integral del dot b dv. This is equal to zero. So del dot b, the divergence of the magnetic flux density is always zero. And this is a very important result. Okay. Why divergence of magnetic flux density is zero? Because magnetic flux lines are always closed. There is no independent magnetic flux lines. And so the total flux through any closed surface in a magnetic field is zero. So if you consider a closed surface like this, okay, so if there are two magnetic flux lines coming out, there will be two magnetic flux lines going in, because the total flux through the closed surface is always zero, and which will give me this equation del dot b is equal to zero. Okay, so I think that finishes our magnetostatics, and I'll give you, along with the assignment, I'll give one assignment on finding the energy density of magnetic fields. Okay, fine. So I think that will conclude our lesson. I know that I have stretched a bit, but it helped me to complete my module one. So make sure you go through these notes. We need to solve some problems regarding this. I'll try to upload some problems, and we'll try to see whether we can discuss all these problems. Okay, fine. So let me take the attendance. So you can call out your roll numbers. One absent.
2.
Okay.
4.
Okay.
5.
Okay.
6.
Sir, 3.
3. Okay. Fine. 6.
6.
Okay. 7 പിടിച്ചല്ലോ. Fine. 8.
8.
അടുത്ത.
9.
Okay.
10.
Okay.
11.
Okay. 12 absent.
13.
Okay.
14.
Okay.
15.
Okay.
16.
Okay.
Dinesh. 17, sir.
Okay.
18.
Okay.
19.
Okay.
20.
Okay.
21.
Okay.
22.